We're going to continue talking about risk and returns when in investing. And the next thing we're going to talk about is what we refer to as ex ante analysis, which ex ante means we're trying to predict the future. So if we're predicting the future, what do we need to know? We need to know two things. One, we need to know what are the events that we're expecting to happen. For instance, we're looking at a stock and we want to say, what will the price of this stock be next year if we have a really good economy? What will it be if we have an average economy? What will it be if we have a bad economy? So we have three events. That's what this is referred to here as the RS, or the HPR in each scenario. Calculate that return. We then also need to know the probabilities. What's the chance that those three economic events happens? And we've used this formula in other videos, but the expected return of that asset is the weighted average of the probabilities times those returns. The variance is based on probabilities, but now we need to square the difference between each one of those events and the mean or the expected return, and we square that. And if we take the square root, that gives us the standard deviation. So here's our example. We have 5 different economic events, and we have predicted A, B, and C here, the rates of return, the holding period returns for each one of these assets, A, B, and C. Now, I have a worksheet that can help us. It's called the standalone risk worksheet. And when we input the probabilities and the returns for each one of these assets, it will calculate the rate of returns for us. So in this case, we look at the expected return. 12.7% is the return for A. 12.7% is the rate of return for B. And asset C has an expected return of negative 0.5%. What is the standard deviation? Standard deviation is our measure of risk. 5.6% for A, 2% for B, 8.72% for C. So even though A and B have similar returns, their risk is different. Obviously, A has higher standard deviation. It has greater dispersion. And those are the things we're going to be talking about throughout this video and many videos to come here when we're talking about investing and choosing assets, choosing and creating portfolios. So let's move on. Risk premium is the difference between the expected HPR and the risk-free rate. It's the difference between what you think you're going to earn and whatever the risk-free rate of return is. This provides us with a concept of compensation for assuming the risk of a particular investment. Now we know the risk-free rate, that's the interest that can be earned with certainty. Typically, we use short-term T-bills from the United States government. We assume they are risk-free rates. Now, we have another type of return. It's called excess return. The excess return is the difference between the actual rate of return and the risk-free rate. So it gives us this actual, if you will, excess return, or the actual compensation that we received above that risk-free rate. Now, another concept that we'll be talking about throughout many of these videos is our tolerance to risk. Now, risk aversion talks about the degree to which investors are willing to commit their money to stocks or to risky assets. Risk aversion has a range of possibilities. The lower the range, the less averse, the less people tend to care about the riskiness of an asset. The higher the number, the more sensitive we are to risk itself. There are a couple of other ways we can calculate returns. We can calculate returns in what we refer to as the arithmetic average. Of course, this means historically you gather all the data, calculate the rate of returns per period, add those all up, and then divide by n. The geometric version is a more intuitive measure that looks at the annual HPR, but incorporates the concept of compound money. So that particular, if you see, you take 1 plus g to the n, that gives us the terminal value. And the growth rate then is the terminal value, 1 divided by nth exponent minus 1. Again, the differences between these is one has the impact of time value, and the other is just a straight arithmetic value. So investors price assets so that their risk premium will be commensurate with the risk of expected excess returns, right? So we want to put a price tag on something so that we're going to get compensated with our expectations. So the best way to measure that risk is by standard deviation of the excess returns, not total returns, but excess returns. In the graph that we had earlier, we can assume that that was total returns. The Sharpe ratio is a measurement that measures the performance of investment managers. It takes that risk premium, the return earned minus the risk-free rate, and divides that by the standard deviation of its excess returns. Again, kind of a difficult number to calculate because we're incorporating two things. One, the top number talks about the risk premium is what we expect, and the bottom part here is the actual standard deviation of what we actually experienced. So it's a kind of a mixed bag here of how we're calculating these values. Moving on to another topic then. Now that we understand how we calculate returns, how we can measure performance for managers, the next thing we need to incorporate then is the idea of other statistics. Are the statistics that we calculated, are they accurate? Do they give us a good picture of real statistical outcomes? The assumption in investments is that the data that we measure, that this data is normally distributed. We have a normal bell curve. Obviously, dead center in the middle is the expectation, or the median, the mean, I'm sorry. So this normal distribution is bell-shaped. Again, investment management is more manageable when returns can be well approximated by the normal distribution. So what does that mean? The data is symmetric. It is stable. Only the mean and the standard deviation are needed to estimate future scenarios. So the statistical relationship between returns can be summarized with a single correlation coefficient. So what does this mean? We assume when we look at data and we want to make some assumptions about what we think is going to happen in the future, we assume that we can explain that really well if we know the means and the standard deviations. That those means and standard deviations are normally distributed. If that is true, then we can also summarize data and relationships with the statistic called correlation. So again, what if these excess returns are not normally distributed? Right? What if the data doesn't fit this definition? The standard deviation is no longer a complete measure of risk. Therefore, the Sharpe ratio doesn't completely measure performance. So, one of the things we may want to look at is the data normally distributed, right? So, we need to measure two other statistics, if you will. The first one is something called skewness. Skewness is a standard measure of asymmetry. What it means is that the normal distribution is tilted left or right. So the formula, look down below, it looks kind of similar to the standard deviation definition, except here we have the cube of the difference between return and the average divided by, again, the standard deviation, but now it's cubed. Then we take the average of that, that gives us skew. Now, in a statistical sense, if something is normal, skewness will be 0. It could be positive, meaning it's leaning towards higher numbers. It could be negative, meaning it's leaning towards lower numbers. Kurtosis measures the height of the curve itself. They refer to this as being fat tails. If you remember, the normal distribution, as it goes out, gets closer and closer to 0, but never ever really touches, but is very, very close. Kurtosis means that it is higher, right? It gets very, very low, but it doesn't really get close to 0. And again, you can see here, it has a different kind of a formula. So, what does this look like? A skewed distribution. Again, this is kind of difficult, but if it's positively skewed, that's this dark line, it's a little bit to the left. So that means it's tilted towards lower numbers rather than higher numbers. Negatively skewed means that it is moving further to the positive as far as the biggest part of, or the highest part of the curve. Kurtosis means if the gray is normal, kurtosis is the measure up. So the higher it is up the curve, then we would say that it has a fat tail. So typically kurtosis should never be negative because it involves the fourth power. And if you square something, it can't be negative. If you do it to the fourth power, it can't be negative. So again, we have this curve, again, that measures the height of the overall distribution. Now, what we'll talk about in a future video is, what does this mean if you're analyzing the data? Does it tell us something about our assumptions and whether we should trust them or not? Look forward to you in the next video.